Good afternoon. Thanks for coming. I'm Dave Mandela. Been working on Ubuntu ARM now for more than 3 years, and it's been kind of an interesting journey. We started out doing development boards for desktops using the newer chips, and we've been moving through into the server space in the last few months. So there's a lot here about that, and then there's some slides on a Panda cluster that I built. But there's a lot more slides than there's really time for, so I'm going to go pretty fast on some of the first ones. And if you have questions about them, great. We'll try to get to them. And the entire presentation will be up on the web, so you all can grab it and look through it at your leisure. So as you can see, there's way too many things on the contents, but we'll try to get to most of them. We started in 2008. We collaborated with ARM directly. Ubuntu is derived from Debian, but we chose not to go the Debian route in terms of Debian's compiled for ARM v4, which is a pretty old architecture, and we went for ARM v7, so we picked up a lot of different instructions, much faster compilation, much faster running chips. And we targeted the ARM Cortex application processors, that's ARM v7. Instead of ARM v4, so it made a big difference in terms of what the chips are capable of. The first release was April 2009. It was using the Freescale IMX51, which is a Cortex A8, a uniprocessor board. The only problem was we had to release on an ARM v5 compilation because those boards, while they were just coming out, weren't available in volume, and Ubuntu builds native, and I had nothing better than an ARM v5 system to build the entire archive. Bit of a problem. Second release, October 2009, we added another board, the Marvell Armada. We upgraded the archive to ARM v6 because we were able to get some better hardware. And we added vector floating point, which we hadn't been able to put on the ARM v5 libraries. The third release we jumped into was in April 2010. We added another board, the TI OMAP 3, and prepped for OMAP 4. We also changed all the hardware within the build system, and we were able to build on ARM v7 native instead of for a lower thing, which gave us vector floating point. We also converted the entire archive to Thumb2, so the instruction set went from a 32-bit RISC down to a mixed 16-bit and 32-bit, which reduced the executable size, effectively making the cache significantly larger. Although the cache size didn't change, but with the instructions dropping, got better use of the cache. And we added Neon, which is a 128 SIMD instruction set. The Neon stuff we put in libraries because, as it turns out, not all of the socks the vendors made supported Neon. So we actually had to do that on runtime, look and see if this chip supported Neon, and then use the runtime to go down into libraries. We also added SMP support. That sounds pretty minor because Linux has supported SMP for a very long time. But in reality, doing SMP support for ARM was a bit tricky in lots of different ways. One of the primary ones were in many applications, as you went through them, there was if statements, if x86 SMP this, 64-bit this. And then when you got down to ARM, it said, there'll never be SMP, why bother? It led to some interesting situations, and we had to take a lot of time to go through and fix the code for that. There was also different things, because we went to the Thumb2, we had to fix assembly code, and I've got some information about that in here. We also changed the desktop to the netbook edition, the EFL library. It was the first time it was released. Here's a picture of it at the time. The fourth release in October of 2010, we added another board, the OMAP 4 Panda boards, which currently are still shipping the Panda board support. We also started working with Grant Likely, supporting the flattened device tree, because we kind of feel really strongly that in the ARM world, where it's at today, you have to compile a kernel for each individual board, not just each individual SoC, but each individual board, because any changes you have to describe to the kernel. And flattened device tree is a really good way to avoid recompiling kernels and pass in the data of what it needs to talk to on the fly, because most buses on the ARM SoCs are not probable. So you've got to tell the kernel, hey, this thing exists, this is where it's at, this is how you talk to it, and that's a really bad idea for a distribution. I can't, on x86, I have a 32-bit kernel and a 64-bit kernel. On ARM, I supported a handful of boards and I ended up with 9 different kernels. That gets really crazy, and separate images for each one of those. Instead of like on x86, I got one image you download and you use, ARM had to have all these separate images. So it really gets to be a nightmare for a distro because upgrades, security fixes, you've got to apply it to 9 different kernels and make sure you catch every one of them and not make a mistake. Human error, really easy to mess these things up. The other thing that makes it very complex, because of the way ARM has worked in the past where all the vendors have held their kernel code to the side and not being upstream, patching the individual kernels was very difficult because security patches that apply to x86 might or might not apply to an ARM kernel, and you'd have to go back and fix the patch to make sure it would fit. So it's very difficult. And the other thing we did is we started working with Linaro. For those of you that don't know what Linaro is, it's a consortium of sorts. It's not really, they said they're not a consortium. It's ARM and many of the ARM vendors, IBM and a few others, who have gotten together to try to solve a lot of the original problems that have been in the ARM situation. They're heading for a merged kernel. They're working on different device drivers, trying to get things unified. They've now picked up flattened device tree. So all these things the Linaro organization is working on and then handing them back to distributions so we can make our lives a little simpler in supporting ARM. So we started back in October. The 5th release, 11.04, we dropped support for a lot of things but kept OMAP 3 and OMAP 4. OMAP 3 we kept supporting for a reason. TI did something really good. Texas Instruments got smart, and OMAP 3 is fully upstream in the mainline kernel. So for a distribution to support OMAP 3, it's really simple. Just pull down the mainline kernel, tell it you're compiling for OMAP 3, and you're done, it works. What a concept. OMAP 4 is still on its way upstream. There's big chunks of it there, but there's still a lot to go. We continue to work with Grant Likely, doing the flattened device tree work. That's a multi-year effort. We've spent several years on it. Linaro is going to spend a lot more years on it. Someday, we'll get to a unified kernel on ARM. It's not going to happen right now, but it will happen, I think, given time. The other thing we did is converted the Ubuntu Netbook Edition to a Qt backend. Here's what the desktop looked like on this release. The 6th release, 11.10, we continue to support OMAP 3 and 4. We added some support in a different way. Working with Linaro, we've gotten an MX53 kernel from them, which lets us support the IMX53 Quick Start board. So we were able to use their work to jumpstart and add some additional support and additional images. As I mentioned, Linaro picked up flattened device tree support. They've got Grant Likely on board, and they're really cranking on trying to get a unified kernel. It's not going to happen today, but it's really coming along. The community, the Ubuntu community also jumped in, and we finally, there's a device called the Toshiba AC100 netbook. It's an ARM device using an NVIDIA chip. And the community jumped on board and got a kernel working, so we picked up full support for that device as well and bought a lot of them because a lot of our developers, it's a really nice device to haul around, as you can see, as opposed to development boards with wires and trying to get through TSA when you're traveling. They get really excited with dev boards. They kind of think the Toshiba is just another netbook, so they don't even think about it, so it's really kind of nice. The other thing that we did, and I think is really important, is we did the first technical preview of Ubuntu Server. Now, folks that have been in the ARM space for a long time are probably going, Ubuntu server? Well, the reality is a lot of the SoC vendors now are jumping into the server space and they're building a quad core or better, 1.5 GHz, 2 gigahertz SoC with SATA support and other things to actually address a 32-bit server market. So we did a technical review. By that I mean we went through the archive and all of what is normally a server package for Ubuntu server for x86, we validated at least that it worked. It compiled and actually ran, because on some of the ARM code in the archive, if you don't actually test it runs, you can get it to compile, but it won't necessarily always do what you think it's going to do. We had pretty good success though, because a lot of the packages for ARM server people have used for years in smaller ARM boards. We went through and tested all the SMP and things like that and got that pretty well sorted. Today, we're working on Precise Pangolin 1204. We'll continue to support OMAP 3 and 4. We should be picking up Marvell and Calxeda. They're the folks right now that have publicly announced that they've got an ARM SoC that's targeted at servers. It's a quad core running at above a gigahertz. The other thing that we've done, we're in the process right now of changing the archive to ARM hard float. When we picked up the ARM archive from Debian originally, it was using what's known as ARM-EL, which is really a soft float. Because the old ARM 4, ARM 5, and ARM 6, there was no guarantee of floating point. On ARM 7, ARM v7, there is a guarantee that you will have a vector floating point unit on every SoC, so we can put in hard float conventions to always call into the floating point engine. The other thing that happened is because of that, they re-looked at the calling convention for C, and the ARM v7 has a lot more registers, and they used more of the registers. So consequently, the archive picked up anywhere from 5 to 30% throughput increase, depending on what the application was. Just about everything, even if it didn't particularly use vector floating point, picked up around 5%. Things that used vector floating point, like fonts, scrolling, and other things, could pick up some amazing things where the scrolling suddenly became very smooth on browsers and other things. The other thing that happened is Ubuntu and Debian became multi-arch, and we became multi-arch clean. Well, what does that mean? It means you can install different arches on the same machine. So on x86, as a developer, if you want to work on some ARM code, you can call down the ARM libraries very easily, and they install in a proper place without overwriting the original x86 libraries you need. So running QEMU and doing development work becomes much easier. The other place that it's very interesting will be in the future. Because I'll be talking about in a moment about ARM64, because the ARM folks are building 64-bit, and we should see in the next 12 months a bunch of chips ARM v8 that'll come out with full 64-bit support. But with multi-arch, you'll be able to run a 64-bit kernel and a 32-bit user space, getting a lot better advantage of your RAM, and only having to put 64-bit applications that really matter to you. Like if you're using databases or other things that need Java that really need large RAM, you can use a 64-bit application. But if you're using apps that don't need large RAM, you can run a bunch of smaller apps that are 32-bit cleanly on the 64-bit space. It's going to give us an advantage to jumpstart the archive, because when we try to build a 64-bit archive, which will start next cycle, it's going to get really interesting trying to do that. Because where they didn't have SMP support before, they never thought ARM would get to 64-bit. So it's going to be quite interesting trying to clean the archive and finding all the assumptions that are 32-bit but not 64-bit safe. So to talk about the archive, as I said, we rebuilt the entire archive. So when we built the ARM-EL archive originally, it took almost 3 months to build it from a standing start. There were 25,000 binary packages built, and that's across the main and universe archives. Those of you that know Debian and know Ubuntu, we have the archives kind of named as main, which is cared about by the canonical folks. Universe, which is cared by the community. Then you got different other ones, binary, restricted, and so forth, where you can put different types of files that aren't under open source licenses. So when we first built it, 25,000 packages, but 3 months. A lot of work went into that, having to resubmit packages, fixing bugs and things. When we built the ARM HF archive this cycle, we built 36,000 packages, but it took us 3 weeks from scratch. Huge difference. A lot of that was due to the ARM v7 hardware coming along and bug fixes that we added to the ARM v7 archive so that we could actually get full throughput. It turns out there was a bug in the ARM SoC design, And if you're running SMP and you had USB drives, which almost every SoC did, it would run at less than half speed on the USB bus if you're in SMP mode. We fixed that. ARM has come out with a better fix, and we've incorporated that this cycle. So really getting better use of the hardware, getting more bugs out of the hardware, we were able to make huge difference. And also, we added some more builders because they're available finally. Now, some fun things. Issues we found compiling ARM v7 for SMP and Thumb. As I said earlier, there were some implicit assumptions that there never would be SMP code. We had to go find all of them and fix it. There were other things that you have to do in assembly using the SWP instructions, conditional variants. They had to be, GCC had to be ported. Use intrinsics where possible, use other memory barriers in other cases. In some of the references I put at the end of this presentation, if you're interested in looking at the assembly code and some of the things you have to do, we have several pages in a wiki that are very well documented if you're familiar with the ARM assembly code on what you need to do differently, what you need to look for, and how they react. So I'm only going to briefly touch on it because I've only got a few minutes, but if you're doing that kind of work, there is a reference in this presentation that will take you to the right page. Review it deeply. We found a lot of interesting things and worked very closely with ARM to get that working the way we expected. Lots and lots of things. Thumb 2. Thumb 2 is a really cool thing, and when you're doing it in C, Thumb 2 just works with GCC. But if there's ARM assembly, Thumb 2 may not work. And depending on how much assembly code and how it was written, you may not even be able to fix it conveniently. So we, in certain cases in the archive, you'll find that certain packages were recompiled with ARM instead of Thumb 2 because we found out we just couldn't take the time to rewrite all the assembly code, or in some cases, quite frankly, we didn't have the expertise that the original vendors had to write the stuff, so we just fell back to the ARM compilation, full 32-bit instructions, and the assembly code works as expected. But you need to take, if you're doing assembly work and you're going to use Thumb 2, which is really handy in a lot of ways, and it does reduce the executable size, it does make better use of RAM, but you got to pay much more attention to getting the assembly code right for doing Thumb 2 work. Hand optimized assembly, codec implementations. This is where I say we just built them as ARM. If we were the experts in the codecs, we might have tried it. We did suggest, and in some cases, Linaro is looking at many of the codecs and rewriting some of them where they can to fix this type of thing. But if you're stuck with a lot of old assembly code, you can just compile it as ARM straight and go for 32-bit. You don't get the advantage of Thumb, but you get working code. Now I want to talk about what I personally think is a real breakthrough in this space, and I'm pretty excited about. ARM server. Now, folks that have been in the ARM space a long time are probably looking at me going, are you nuts? Why would it matter? x86 has got the power, it's got huge horsepower. Why does it matter? Well, it matters because of power. There are data centers that cannot get any more power. They've already got as much power going into them as they can possibly get. So they can't add more machines. They've got lots of chillers to cool down the space. I don't know, any of you that have walked into a data center know how cold they keep it to keep the temperature down for the machines. ARM has the advantage of being very low power, so on throughput per power consumed, ARM beats the x86 considerably. For example, looking at the OMAP 4 processor as an example. Now granted, it's absolutely not an ARM server CPU, but the Panda board itself draws a maximum of 4 amps if everything is turned on it at the same time. That's all of its DSPs, that's all of the CPU running wide open. The same x86 would run something 80, 90 watts. Looking at some of the ARM SoCs that are designed for server workloads. They're putting SATA on the main bus, not through USB. Panda, everything goes through the USB, which is kind of sad, but it's a phone chip. These server chips are being designed fundamentally from the ground up to utilize the throughput of proper buses. As I say, 64-bit support is coming over the next 2 years. There's virtualization. All of the virtualization will be working. ARM is working on some of it right now, KVM. So they're really doing some massive work targeting the server market. They think that's going to be a major breakthrough area, and I think they may well be right. Just to look at it, to power and cool servers worldwide, and again, most of those are x86, some are other machines. It's a huge amount of power in a data center. When you start looking at being able to put ARM in there to do certain loads that ARM makes sense for, you can cut the power by 3 or 4 times what the x86 consumes. And so you put more machines in there for the same power, and you reduce the heat load so you can turn down the chillers and not have to suck as much energy through the chillers, so you can again put more machines in the same space. Again, the OpEx drops are based on power and cooling, so there's huge benefits when you're starting to look at 5 and 14 watts on a server as opposed to 50, 60, 80 watts or more. So why Ubuntu server? And I work in the Ubuntu community, been doing this ARM stuff. ARM is really interesting because they're going to break into these highly dense servers. And Ubuntu is really good in that area. We've got a lot of web serving apps, and we don't charge for things. Canonical does not charge for updates and things like that, and that really works in this marketplace. Ubuntu is already natively compiled for Cortex-A9 with Thumb 2, so that Cortex-A9 means it's an SMP chip. Doesn't say how many it may be. It could be 2, 4, or more. But we're already compiled. We've got 3 years experience in it, and it's really coming along. So we've got some real head starts in this area. So here is a quick picture of a Marvell server SoC. Now this is public information. They've got one chip, it's quad core. Their total power consumption at full boat is 14 watts. They're looking at putting these into very high density servers, more than 500 servers per cabinet, including drives. So this lets them really get a lot of information, a lot of servers in a very dense area. They're not the only players on the block. Another one is Calxeda. You've probably heard their announcement if you're paying attention in the ARM space not too long ago. They've got their own SoC, which is quad core. They say it sucks down about 5 watts. They're looking at extremely dense things, but they've got SATA, PCIe, Ethernet, and they're looking at 10 gig Ethernet, 5 channels of 10 gig Ethernet on each SoC. They also are looking at full controller abilities, so you can remotely control it out of band with each SoC, not having a separate card like today we do on most of the x86 servers. So they're working, it was announced already that they're working with HP and others, but you're looking at an order of 72 servers per rack unit. If you start doing the math on that, it gets really crazy. But not only that, on their particular SoC, they need 3 IP addresses per sock. And they've got 4 socks on each board and then lots and lots and lots of boards. If you start putting 3,000 servers in a rack, and then you boot that thing and it wants DHCP service, 3,000 times 3 addresses, and then you've got racks and racks and racks of these in a data center. Got a little management problem there, and you're going to have a little bit of delay on boot up while you've got contention for the DHCP server. So there are things that are going to have to be done. I'm not saying that we're ready for prime time, but I'm saying we are starting to work on this problem with the vendors. And I think that the community that'll be jumping in on this, these vendors are also going to be making dev boards that the community can get their hands on. It's going to be a very exciting time in the server space when we start playing with these highly dense machines that use 5, 10 watts per SoC and got densities like this. On the other hand, I'm taking it with a grain of salt. When you start adding that many servers, even at 5 watts, you have a heat problem. If you do the math, that's a whole lot of heat that you got to move out of that machine. Still magnitudes of order less than you couldn't come near putting that many x86 chips in a box. You'd think it'd start glowing. But it's a real interesting place to be looking at. One of the things that Ubuntu has that I think is a real win in this space is something called Juju. It's Ubuntu configuration management. They've been working on it for the cloud, so that you can deploy bunches of servers and say, I want 20 machines to be a web server, I want back-end databases, I want all these things done. Juju will do that. As I say, it was meant for the cloud, but we've tested it on ARM servers, and it actually works. So I think that's one potential solution. It's all open source. I think it's pretty interesting stuff. It's kind of an intersection of cloud and ARM, but I think it's going to be important when you've got that many servers that you've got to manage. It's a bit more headache than I ever dreamed of. Juju uses these things called charms to describe how to deploy different apps, and these are just a bunch of the different apps that have charms today that you can download and deploy with. Ubuntu server tomorrow. This is what's happening today. We're working with Calxeda. It's 32-bit servers. It's not 64-bit servers. So we're doing that today. In April, we expect to do a release that'll have support for them, assuming that all the hardware is ready in the ARM space. Those of you who played in this space, hardware sometimes lags their expected delivery dates. So we'll see where we're at then, but we're looking pretty good for having some amount of support in there for these 32-bit servers. But, you know, there's the 64-bit world, and ARM is going after that as well. So on our 8th release, I'm going to start talking about the future, and as some people in this room know who have written about making projections for the future year, you can pretty much guess how accurate these projections are, but I'm going to give it my best guess. We'll continue supporting Calxeda and Marvell servers. We'll be targeting heavy optimizations for best power performance per watt. We will also be the first OS to support the ARM Cortex-A15. That has virtualization, so that KVM and Zen support will be there. That's a pretty exciting thing because up till now there has not been hardware support for virtualization in ARM. The A15 will be the first chip that has that. There's also large physical address space for up to 1 terabyte of RAM in this A15 chip, and we'll have support for that. I'd rather it was true 64-bit, but it's a start. 1204 is supposed to be an LTS. For x86 it will be an LTS. For ARM we'll see. We're trying for making an LTS on ARM server. I don't know if the hardware will be available, but certainly as the hardware becomes available over the next 6 to 12 months, the LTSs get dot releases for hardware support, and we will do hardware support for A15 and other things into the LTS at 1204. So we'll be supporting that. The other thing that we'll be looking at is we're going to start the work for ARM v8, 64-bit. I really expect that we'll have a kernel, we'll have a tool chain, and we'll have QEMU or some type of virtualization so we can start the support in Ubuntu for a 64-bit archive. And that'll be pretty exciting stuff. As I say, I expect that to be a huge amount of work. It'll probably take a full 6-month cycle to begin to get an archive together as we go through all the packages, validate that they work on 64-bit, fix the problems, fix the assembly problems. There's a huge amount of work here, but we're really looking forward to it and pretty excited about it. 1304, 1310, client support, the desktop stuff will continue. The ARM 32-bit server releases will continue. We'll see a lot more enterprise ARM support. And we'll get Cortex-A7, which is this crazy thing of a bunch of very fast cores with slow cores. And it'll shift down to the slow cores when the machine idles and shift back up to the fast cores when there's work to do. I don't know how that's going to work, but we'll support what they come out with. We'll be the first OS to support ARM v8 true 64-bit SoCs. This is going to be a bit of a problem. One of the things that it's looking like is UEFI boot method will need to be supported for ARM64, and it'll start getting rid of U-boot, MyBoot, RedBoot, and all these other crazy bootloaders. Whether or not that's a good idea or a bad idea or how you feel about it personally, I'm going to step back from that discussion, but there's a lot of work there to get that all working, and also to get it working because Microsoft is paying attention to the server space, and they're planning on being on the ARM 64-bit servers. So we're going to have to play nice with them, and it'll be very, very interesting. And I'm running out of time, so I'm going to keep zipping through. We're going to try to make the best use of RAM. I mentioned that we'll do, with Multi Arch, we'll be able to do a 64-bit kernel, do a 32-bit user space where it makes sense, add support for 64-bit user space or a mixed user space depending on what you're running, and we'll have that fully supported. It'll be quite interesting to get that going, but feel pretty solid about it. I mentioned that we support the Multi Arch, so that'll do the 32-bit, 64-bit cleanly. We're still shaking some of that out. There's corner cases that Debian and Ubuntu are finding in the 32-bit space, not even relating to ARM, but x86. But we're getting it all sorted out so that we'll be able to do it on ARM as well. Moving on, again, 2013 UEFI, the Multi Arch. We'll continue in 2014 for client support. We'll see real 64-bit hardware by that point, and we'll have 32-bit and 64-bit images. I'm really hoping that by that time we'll have a more unified kernel, and maybe in some SoC families we'll be able to get a unified kernel booting across the SoC families. I'm not sure we'll get to a unified kernel that'll boot any ARM device, but we're working on it. I think we'll be much closer by 2014. All right, Panda Builder. We needed to be able to build a lot of these packages really rapidly, so deploying a lot of Panda boards, but they're dev boards, lots of wires, it's a mess in a data center. So we put 10 pandas in a control panda in a 4U case. The case has cutouts for RJ45 keystone connectors, which are used for Ethernet and serial outputs. There's a 200 amp 5 volt regulated power supply to run all the pandas. That was really cool till I suddenly realized at 5 volts with 200 amps you can weld if you short. That took some real rethinking real rapidly to get a fuse panel in there, because I had first naively just ignored the need of a fuse panel till I did the math and went, oh yeah. There's a 5 amp small 12 volt regulator just for case fans, because when you got that much hardware in there and laptop drives, you got to move some of the heat out. There's not a lot, but you really do need to move it out. Each Panda is serial Ethernet ports brought out. Each Panda boots from a USB from the control Panda. You can talk in the Ubuntu channel or on the TI channel. There's a little known property of the Panda board. It will poke on the USB first. If it gets a proper response, it'll then set up to take a bootloader and kernel over the USB. Otherwise, it goes to the SD card to boot from. So you can do boots over USB, you just have to know the magic. We added a serial control relay to control each Panda's power. Ran into a slight problem. The Panda board has an interesting bug. It takes 5 volts in to run the board, but if you have a powered USB device plugged into it, the USB port works slightly incorrectly. It supplies power to run things, but if power is being supplied on the far end, it'll keep the Panda booted. Really makes a problem when you're trying to turn off the Panda to do a hard reboot, and you got a drive out there that's holding the Panda lit. Yeah. So we added a 12 volt relay to be able to hard knock down both the Panda and the powered hard drive, so we could control this crazy thing. So here's some pictures real quickly. The Panda case, those square holes on the top, on the back panel are for these specific RJ45 keystone connectors. They just snap into the hole, so they're really convenient if you're trying to do things. Panda stack, just using metal offsets to put 11 Pandas together. Sorry that one's not real clear, but my blog URL is in here. You can look at much clearer pictures. That's the serial control relay. I put a rather large one, larger than I needed. The next board will be smaller, but that lets us control each individual Panda. There's the big power supply. It doesn't look huge, but 200 amps. Yeah, nice way to weld. You've got to stick all these drives into a case, and you need USB cases because the Panda doesn't do SATA, so I had to go out in my garage, and I live in Texas. Let me tell you, the summertime in Texas in your garage, doing metal work with a pop riveter, drill press, and a bandsaw, yeah, that's a way to work up a good sweat. But using it was 5/8 U-channel, aluminum U-channel, you can build little stacks like this and get everything mounted relatively neatly. And it helps pull the heat off the hard drives because that whole thing turns into a heat sink. Just made it. Here's the resources. This, as I say, will be available to everybody to download. There's lots of good information here, particularly, like I say, if you're doing Thumb-2 work or porting to ARM, go to those pages. There's a ton of information that will save you a lot of time and headaches. I hope that you all join us in the ARM travels. It's going to be a lot of fun. I'm hugely excited about 64-bit server, and I think it's we're a little early, but we can open up for questions because I've reached the end.
Okay, so has anyone got any questions? Hands up. Nobody? All right, great.
So I know in one of the kernel versions previously, they added support for the swap and I think other instructions in the kernel. So I've actually had it was an ARM v5 device, and I know that when I enabled that in the kernel as an option, some things just broke badly. Can you talk about any experiences with those kind of things? I'm just interested.
Well, we've been completely avoiding ARM v5, ARM v6. What we did in Ubuntu, recognizing that some of the instructions aren't going to work on the old architectures, where we did patching to accommodate Ubuntu and Debian in the ARM v7, or really Ubuntu, but so we've got a lot of if-defs and we work the code so that if you're using it on older platforms on ARM v5, ARM v6, or even ARM v4, the proper old instructions are still there, but we just recompile it the other way for making it with ARM v7. And we'll do the same thing with ARM v8 when we get there. I don't know what we're going to have to change, but I'm sure there'll be a lot of changes. Next.
Will the April 1204 LTS release support the IMX53 Quick Start board?
Will the next release support the IMX53? Yes. We will continue our support for that. We are working with Linaro for a kernel for the IMX53 series for the Quick Start. Linaro is, we expect to get a kernel from them quite soon that will be a 3.2 kernel, which is what we're supporting for the 1204 release. But we've been in close contact with them, and I'm expecting that kernel anytime in the next couple of weeks. Linaro has what they call Linaro Connect in February. I think certainly by the second week of February at their Connect, we'll get the right kernel. We will fully support that board.
Okay, any more questions?
This is slightly off topic, but how do you think this fits in with the Ubuntu TV strategy announced at CES this year?
It'll be kind of interesting. I have not been working with the Ubuntu TV strategy or any of that, but when you look at the TVs today, most of them use ARM chips as the core of the TV. So I think it's going to be quite important that a separate team in the community on Ubuntu has been working on ARM, and we've got all the development experience to be able to help support the guys that are doing all the work. The key piece is their user space. We did some testing because we were asked to do some quick testing, and we took their user space demo, and we were able to port it to the Panda board with almost no work at all, and on the IMX53 as well. So their user space is pretty clean as long as you've got a good solid kernel under it with the standard the Ubuntu interfaces that we have. The user space seems to work pretty well. So I think it ties together pretty well. I wish I'd been more involved with it, but Canonical's a pretty big company, and I was completely off on the side. I had no idea what was going on. Oh, got a question back there, I think.
Any more?
You mentioned the cross-collaboration between Ubuntu and Debian with the work you've been doing. What other community groups and distributions have you been working with?
Well, as I say, we have been working with Debian. We've been working with Linaro. Recently on the server work, we've also been collaborating with Red Hat. As we get into the 64-bit space and UEFI and these other things, and even in the 32-bit space, it's important that our distributions remain compatible so that people that have applications in the user space can use them on Red Hat or use them on Fedora or Ubuntu or Debian. So we've been collaborating with those folks as well to make sure that we've got our loaders and all the binary bits in the right places so that any particular binary application in the user space will find the appropriate thing where it expects it and will work. So we have been working with everybody on this. I think it's key that we continue to do that because we really need to it doesn't need to be Ubuntu only, it doesn't need to be Debian only, it needs to be Linux supports ARM and supports it really, really well.
Sorry, this is often a slightly different area. I love the stuff you brought up about Thumb 2. I did a bunch of development work on ARM and MIPS16 and some other low-level architectures about 10 years or so ago. What kind of level of benefit are you seeing in terms of memory utilization difference versus like pure ARM versus Thumb 2?
Memory utilization on Thumb 2 versus ARM, we're seeing generally about a 30% benefit. 30% less RAM is used on Thumb 2. It's not 50%, would have been nice, but it is a mix of 32-bit and 16-bit instructions, so it's about a 30% savings. We see that in the cache, we see that in main memory, so it was worth doing. We get faster load speeds, again, around 30% better. It's really about the number. Does that answer your question?
Yeah. Any more? At the back.
Way up at the back.
So user space is compiled as Thumb 2 when possible. Is the kernel also compiled as Thumb 2?
We have not been compiling the kernel as Thumb 2. It can be done. We're looking at it, but we've been doing the kernels as ARM.
Right.
So that it's just, we haven't really been paying attention to trying to get that 30% smaller. We could, we've tested it, it does work. We just haven't bothered at the current time.
Okay.
Okay, thanks for that. Has anyone else got any more questions here?
It's short. Any comment on secure boot, UEFI and ARM?
Sure. Comment on secure boot, UEFI and ARM. Yeah. I'm personally involved in working with some of this, working with ARM and other groups to look at the UEFI situation, secure boot. Obviously, we oppose Ubuntu, we oppose a secure boot that does not allow the end user to choose what they might want to boot. Now, the way the Windows 8 requirements are set up, their logo requirements, they talk about x86, they talk about ARM on the client user space, and there's no guarantee on the client user space that they'll be able to turn off the secure boot and load their own stuff. We are going to be working very, very hard. I know Red Hat is active in this space, we're active in this space, and other, Linaro and ARM themselves are all active in trying to make sure that on the secure boot you will be able to turn it off like you'd be able to on x86 and boot your own OS. I don't know how it's all going to shake out, but I know that we're highly active. As I say, I know that Red Hat is as well, where we go to the same places and we make the same noises. So we're going to work hard to make it a reality that you get to be able to choose what you're doing, but it's not there today. The funny part is it's not stated, okay? It's not part of the Windows 8 logo. So we're trying to get it stated. It makes me very nervous when there's something left ambiguous because that kind of leaves a door for somebody to lock it down and go, well, but it never said what we were going to do. So we're trying to make sure it gets stated.
Have you had any interesting challenges with trying to get the changes that you're making back upstream into the associated projects? And, is there any particular areas that have been more challenging than others?
Have we had any trouble getting changes back upstream? For the most part, no. Most of the folks upstream have been very interested in taking our patches. Early on, we had a little bit of trouble because they couldn't validate what we sent them. They couldn't get boards. So they had to kind of take it on trust, and we worked very closely, sending them a patch. They'd send us code, we'd run it, validate it, and send it back to them, go, yeah, it worked, or no, it doesn't work. Now, pandas are pretty readily available, which is our standard platform for testing. It's SMP. It is USB on drives and everything else, but it's a good platform, easily available. Also the IMX53, but that's a uni processor, so you need to run on both. You need to test the SMP. The IMX, however, has an SATA interface, so you can test on higher speed drives, but you only have one processor. We've had a few projects that have rejected our patch and then supplied their own. One that jumps out at me was Mono. Mono, the patch that they proposed didn't actually work, and we're still working with them. Hopefully we get them to either take our original patch or maybe work with us to get that sorted. Right now on Ubuntu, we turn off SMP processing for Mono. It's the only way it'll run. At least, let me restate that. It's the only way it'll run safely, because it kind of sort of works, but then sometimes it doesn't. Does that answer your question?
Any more questions?
Good. Just a few more minutes if there's any more questions.
Nobody? Okay, we'll wrap this up. Can everybody give a hand to our fantastic speaker for today?
Thanks a lot. I appreciate it. Thanks for taking the time.
And on behalf of the conference team, I'd like to present you with this.
Thank you.
Thank you very much.